Okay, welcome to video 1.5. Um, Here's what I'm going to do. I'm going to end this with, I think, with 1.6. 1.6, what I'm going to do is describe a few bits of terminology for green. So I want to see it from me first, that terminology. Then it'll be a little bit easier to read green if you've seen that. Now, to get to 1.6, I'm going to describe here 1.5, a concept, okay? And this involves just the following fact, okay? It's the notion of um, if we have a strictly increasing function, then that function preserves order. Okay, now here's what I mean by that. So um, assume h, call the argument z, is strictly increasing. Okay, assume h of z. Can you see that h of z is strictly increasing? Okay, so here's what that means. Um, if we have, if this is z and this is h, and let's suppose we have two values of z, call it z1 and z2. Okay, we have if z2 is greater than z1, then necessarily h of z2 is greater than h of z1. Okay, that should be obvious. If this thing is strictly increasing, z2 is bigger than z1, then z2, h of z2 has got to be higher than h of z1. Okay, now also, let's suppose instead that we have a bunch of z's, and let's say the biggest of the z's is, let's call it z8, but we also have z3 here, z4 here, z5 here, z7, and so on. Okay, so we have if z8 is the maximum of all the zi's, then h of z8 is the maximum of all the h of zi's. Okay, so in other words, if here's, the h of zi's are the height of all these dots. Okay, z8's got to be the highest of all those. Okay, so in other words, if h of z is strictly increasing, it preserves order. Okay, so if if one z is bigger than all the rest, then h of that z will be bigger than all the rest. Okay, so what that means is the following. So if we have h of z is strictly increasing, okay. Okay, let's erase that. H of z is strictly increasing. Now, suppose L of theta is some function. Okay, in a second I'm going to go back and I'm going to call L as a likelihood function, but it doesn't have to be that now. Suppose L of theta is some function. Suppose L of theta is maximized when theta equals theta hat, some theta. So L of theta theta's here, theta hat is here. So L of theta looks something like that, okay? It's a maximize when theta equals theta hat, okay? If that is true, okay, if L is maximized when theta equals theta hat, then um, H of L of theta is also maximized when theta equals theta hat. Okay. The idea is that H preserves order. Okay. Because it's strictly increasing. That means it preserves order. So if theta hat is the maximum, so of all the possible L of thetas, L of theta hat is the maximum of all those. Let's think of all the possible values of H of L of theta. Here again, it's going to be maximized. This thing is going to also be maximized when theta equals theta hat. And that's just because of that H preserves order. Okay. I'm kind of waving my hands, but hopefully that's intuitive and you can see why that's true. Okay. So that is the case. So if L is maximized when theta equals theta hat, then H of L hat is also maximized in that. Okay. Now, all we're going to do now is the function log, natural log of something is strictly increasing. So everything I said about this very general function H has got to be true for this particular function, natural log. Natural log looks like this. Okay. Function, it's strictly increasing. Okay. So that means if theta hat maximizes L of theta, then theta hat also maximizes log of L of theta. Okay. All right. So hopefully that is intuitive. Okay. Remember this. I'm going to use it in the next lecture, and Green uses that all the time. In fact, anytime you're doing maximum likelihood estimation, the econometricians will always say, let's instead take log of L. Okay. It's got to be maximized at the same value because log is a strictly increasing function, so therefore we can do this trick. Sometimes it's a little easier to take the log of the likelihood rather than the likelihood, okay? So that's where we're going, okay? All right, so this was lecture 1.5, okay? I'm going to use that in lecture 1.6. See you there.